Welcome back to Explained, the show that takes those complex topics and breaks them down. Today, we're diving deep into the network layer. You know, the internet's postal service?
Yeah, you could think of it like that. It really is the unsung hero making sure all those data packets get from your device to wherever they need to go. Like Google servers, for instance. It doesn't matter what website you're on or video you're streaming.
Right, exactly. But instead of streets and zip codes, we're talking IP addresses and routers. And speaking of IP addresses, have you ever thought about how your device even gets its IP address? It's something I never really think about, but
Yeah.
it just sort of works.
Yeah.
Let us know down in the comments how you think that happens.
Well, it's actually not magic, even though it kind of feels like it sometimes. There's this system called DHCP. It stands for Dynamic Host Configuration Protocol. And it basically acts as this like automated IP address dispenser.
So it's like a, what is it? Like a digital welcome map for devices when they join a network.
Exactly. Your device is basically shouting out, hey, I need an IP address. And a DHCP server hears that and responds with an offer. It'll include things like the network's gateway address and some DNS server information.
Wow. It's pretty cool how all this is happening in the background, and we don't even realize it.
Yeah, for sure. And DHCP isn't the only really cool thing that's happening at the network layer. Think about routers for a second. Those little boxes that connect all our devices. When you think about a router, what do you picture?
Honestly, just a little box.
Yeah.
Blinking lights, a bunch of cables sticking out the back. That's my mental image.
I think that's most people's, honestly. But there's a lot more to it happening inside that box. It's like a miniature airport.
Yeah.
With all the packets arriving, they get inspected and then directed to the right outgoing flight, to their final destination.
So it's not just a traffic cop. It's a whole travel agency for data packets.
Yeah. Exactly. And just like an airport has these different areas, right? For arrivals, departures, baggage handling, a router has all these special components too, like input ports, a switching fabric, output ports, a routing processor.
Okay, let's break that down a little. What exactly are all of those components doing?
So imagine a data packet arrives
Yeah.
at a router's input port.
Right.
The first thing it does is, it gets checked for errors, and its time to live TTL gets decremented. It's kind of like a countdown timer for how long that packet can be wandering around the internet.
So that prevents packets from just getting lost forever in cyberspace.
Exactly. Then comes the really important part, figuring out where this packet needs to go next. So the input port uses something called the longest prefix match rule to find the most specific route in its routing table, which is essentially a map of the network.
So the router's solving this logic puzzle to get that packet where it needs to go.
In a way, yeah. And all of this, the
Yeah.
inspecting, the routing, the forwarding, it happens so fast because of specialized hardware.
It really is amazing how much is happening in that little box. I'll never look at a router the same way again.
Yeah, me neither. And remember, there are millions of these routers out there, all working together to move your data all over the globe. They have to rely on clever systems to do that efficiently, like IP addressing and subnets.
Right. IP addresses, those are the unique identifiers for
No.
every device on the internet.
Yeah.
But subnets, I'm not as familiar with those.
Yeah.
What are those exactly? Are they like neighborhoods of IP addresses?
That's a great way to think about it. Subnets let us group devices together that communicate frequently, which makes routing a lot more efficient. It's like having all these smaller postal routes within a big city.
That makes a lot of sense. But with, billions of devices coming online all the time, how do we make sure they all get a unique IP address? I've heard of something called IPv4 exhaustion. Is that what you're talking about?
Yeah, it's a huge issue. That's where NAT comes into play. NAT stands for Network Address Translation. It's like having a single phone number for an entire office building. That way, all those different devices can share a single public IP address.
Oh, okay. So that's how my home Wi-Fi can connect all these different devices without needing a separate IP address for each one.
Exactly. NAT's kind of like a smart receptionist, directing incoming calls to the right device within the network, based on these things called port numbers.
Wow. It's such an ingenious system. But I imagine it creates some challenges too, right? I mean, it can't all be smooth sailing.
Oh, you're absolutely right. Imagine trying to call someone inside that office building, but you only know the main number. That's essentially the problem we run into with something called NAT traversal. Connecting to devices that are behind a NAT can be really tricky.
Oh, that makes sense. So what are some of the solutions to this NAT traversal problem? Make sure to follow Explained to get more in-depth dives like this one. We have lots more great content on the way.
Thanks for the plug. There are a few ways to deal with the NAT traversal problem. One is something called static port forwarding. where you basically map specific ports on the public IP address to certain devices inside the network.
So it's like telling the receptionist, hey, any calls that come in on extension 123, send those over to Bob. Bob in accounting.
Exactly. But managing those mappings can be a real pain, especially when you have a really large network. That's where other protocols come in, like UPnP and relaying. They provide more automated solutions for dealing with NAT traversal.
Wow. It's constant back and forth, isn't it, between making the network efficient and making sure all the devices can connect without any issues.
Yeah, it really is.
Like,
But, and let's not forget about the real heart of routing, the routing protocols themselves. Those are the languages that routers use to talk to each other and to build their maps of the internet.
yeah, I've definitely heard these terms thrown around before. OSPF, BGP. What's the difference between them?
Okay, so think of it like this. OSPF, that's for local directions, like within a neighborhood.
Up.
BGP is for navigating between, say, different countries. OSPF stands for Open Shortest Path First, and it's a link state protocol. It basically builds this really detailed map of the entire network. It's like a road atlas, but for data packets.
Okay, I'm following you. So each router shares information about its local connections,
Yeah.
and then they piece it all together into one big, comprehensive map.
Precisely. And they use this thing called Dijkstra's algorithm to calculate the most efficient paths to any destination within that network.
So it's like they're working on this big collaborative mapping project, but for routers.
Yeah. Now, BGP, or Border Gateway Protocol, that's a whole different animal. This one's used for routing between these things called autonomous systems, which are like these big internet regions managed by different organizations.
So BGP is how data travels between, let's say, Google and Facebook's networks.
Exactly. BGP is all about exchanging reachability information. So which networks can an AS actually reach? And it's about establishing these trust relationships between different ACEs.
It's like a diplomatic agreement for exchanging data between internet superpowers.
Uh-huh. Yeah, I like that. BGP doesn't just consider the shortest path either. It also looks at things like policy preferences and business relationships between these different ACEs.
Wow. It's fascinating how all these real-world politics and economics come into play. With these routing decisions, it's not just about the technical stuff.
It's a complex interplay of factors that makes the internet so dynamic and so interesting. Oh, and let's not forget another super important piece of the puzzle, ICMP, the Internet Control Message Protocol.
Oh, right. ICMP. I've used some tools before that rely on ICMP, like ping and traceroute. What's so special about this protocol?
ICMP is like the internet's built-in toolkit for troubleshooting. It helps diagnose network problems and shows us how packets are actually moving around.
So it's like the network layer's version of a mechanic.
Exactly. Like ping, for example. That uses ICMP echo requests to check if a device is reachable, and it can measure the round-trip time, which gives you an idea of the network latency.
Like sending out a sonar pulse and seeing how long it takes to hear that echo come back.
Precisely. And traceroute uses these ICMP time-exceeded messages to map the path a packet takes to get to its destination. It's like dropping breadcrumbs along the way.
Oh, okay. So you can actually see all the routers that packet hops through
Yeah.
on its journey across the internet.
Exactly. ICMP lets us peek behind the curtain to see these hidden pathways of the internet and helps us identify any bottlenecks or routing loops that might be causing problems.
It's crazy how these seemingly simple protocols can play such a big role in keeping the whole internet running smoothly.
I know, right? And there's still so much more to uncover. The world of the network layer is vast and it's constantly evolving. There are new technologies like software-defined networking, SDN for short, that are completely changing the game. But we'll save that for another deep dive.
This has already been such an eye-opening journey through the inner workings of the internet. We've learned about IP addresses and routers, routing protocols, and how they all work together to make sure that our data packets are getting where they need to go.
It's a really complex system, but it's incredibly well orchestrated too. It underpins our entire digital lives. And that brings us to the end of part 1 of our deep dive into the network layer. Welcome back to our exploration of the network layer.
Yeah, picking up where we left off with those routing protocols. So important.
Right, those are the languages that all the routers use to chat with each other and, keep their maps of the internet updated.
Yeah, we talked a little bit about OSPF and BGP,
Yeah.
but there's a whole bunch of different routing protocols out there, right?
Oh yeah, definitely. It's a whole family. Each one has its own kind of strengths and weaknesses. So some are better suited for different types of networks.
Okay, so let's start with link state routing protocols.
Yeah.
And it's specifically OSPF. Open shortest path first.
OSPF. Think of it kind of like a super organized neighborhood association.
Okay, now I'm intrigued. What do you mean by that?
Imagine if every single house in this neighborhood meticulously reported on the condition of its sidewalks and streets, to this central bulletin board. So everybody has this perfectly clear picture of the neighborhood's infrastructure.
Yeah, okay, I see where you're going with this. So everyone's got the same information.
Exactly. So in OSPF, each router broadcasts all these details about its directly connected links and the costs of those links, which could be things like bandwidth, delay, other factors.
Okay, and then all this information is flooded throughout the whole network. So every router ends up with this complete map.
Right, precisely. They build this thing called a link state database. It's basically a shared understanding of the network's topology.
And once they have that map, how do they actually figure out what the best paths are to get the data where it needs to go?
That's where Dijkstra's algorithm comes in. It's like this classic algorithm for finding the shortest paths in any kind of graph.
So it helps the routers find the most efficient routes based on all those link costs that we were talking about.
Exactly. And OSPF is known for being really fast and efficient, especially in those larger networks where having accurate, up-to-date information is absolutely critical.
So it sounds like OSPF is kind of like the gold standard then for routing within, like a company's network.
Yeah, it's definitely a popular choice for sure. But there's another whole category of routing protocols that we should talk about. Distance vector protocols.
Oh yeah, like RIP.
Right.
Routing information protocol. I remember you were comparing it to.
Yeah.
Like asking your neighbors for directions.
Yeah, that's a good way to remember it. Instead of sharing these detailed maps, like with link state protocols, routers using distance vector protocols just tell each other how far they think it is to a bunch of destinations.
So it's kind of like a word-of-mouth routing system.
Exactly. Each router maintains what's called a distance vector, which is basically just a list of destinations and their estimated distances.
Okay, and then they're constantly sharing these vectors with their neighbors.
Yeah, they do that periodically. And to update their own distance vectors, they use something called the Bellman-Ford algorithm.
I've definitely heard of that algorithm before, but
Yeah.
to be honest, I don't really remember how it works. Can you give us a quick refresher?
Sure. It's basically all about comparing notes with your neighbors. So let's say your neighbor says they know a shorter route to the grocery store. Then you'd update your own estimate accordingly.
Oh, okay. So it's like this constant process of gossip and information exchange,
Oh.
hopefully leading to these accurate routing tables.
Exactly. And distance vector protocols are usually simpler to implement. They require less overhead than link state protocols, so they're often a good choice for smaller networks.
They do have some quirks, though, right? You mentioned that count to infinity problem. I think that's what it was called.
Ah, yes. The bane of distance vector routing. It happens sometimes when a link fails somewhere in the network.
So like if a bridge collapsed in our little neighborhood analogy.
Exactly. Now, with link state protocols, everyone would hear about that really quickly, and they could adjust their maps right away.
But with distance vector, it's like the neighbors keep telling each other these outdated directions.
Yeah, that's a good way to put it. They might keep increasing their distance estimates, and they get further and further from the actual truth.
So their routing tables get stuck in this loop of these constantly increasing distances.
Exactly. That's the count to infinity problem. The distance estimates basically spiral out of control because everyone's working with stale information.
That sounds like a recipe for disaster. Total routing chaos.
It definitely can be. Luckily, there are some techniques to help mitigate this problem, like split horizon and poison reverse.
Split horizon. That sounds familiar. Isn't that the one where you don't tell your neighbor about a route that you learned from them in the first place?
You got it. It's like saying, hey, don't tell me about the park. I literally just came from there.
Uh-huh. Okay. And then what about poison reverse?
That one's a little more drastic. It's where you basically advertise an infinite distance for a route that you know is unreachable.
So it's like specifically warning your neighbors about that bridge that collapsed.
Exactly. And using these techniques can help prevent those endless counting loops. And eventually, the distance vector protocols will converge on the accurate routes.
It's a good reminder that even with something that seems relatively simple, like these routing protocols, things can get really complex really fast.
Oh, absolutely. And we haven't even touched on some of the more advanced features of these routing protocols, like route aggregation and multipath routing.
Yeah, route aggregation. That one sounds pretty interesting. It's kind of like grouping together nearby destinations on a map to just simplify things.
Exactly. It's a way to shrink down those routing tables and make the routing decisions a lot faster. It's especially useful in large networks.
So instead of listing out every single house individually, you just say, hey, this entire block.
Precisely. And multipath routing lets routers use multiple different paths to reach the same destination, which can really improve resilience and load balancing.
So if one path gets super congested, there's always a backup route ready to go.
Exactly. These are just a few examples of how routing protocols have evolved over time to be able to handle the internet's ever-growing complexity.
It's honestly mind-blowing when you think about it, how much intelligence goes into making sure that all our little data packets find their way all over the globe.
It's a huge testament to all those engineers and researchers who've built and continue to improve these systems. It's really quite remarkable.
Speaking of ingenuity, we briefly talked about software-defined networking, SDN, in the last part. Can you remind us why that's considered such a game changer?
Sure. SDN is all about giving us more control and more flexibility over how our networks actually operate.
Right, and I remember you were talking about separating the control plane from the data plane. Can you break that down for us again?
Yeah, so traditionally, routers have been like these self-contained units. They make all their own decisions about how to forward packets.
So they're kind of like these independent drivers, each one navigating their own little stretch of road.
Exactly. But SDN introduces this central controller. Think of it like an air traffic control tower for the entire network.
So now instead of each router making its own decisions, they're all getting instructions from this central authority.
Precisely. And the central controller has a global view of the entire network, so it can program the forwarding behavior of each individual router.
It's like having this master puppeteer controlling all the strings for all those little router puppets.
I like that. That's a good one. Yeah, SDN centralizes all of the network management, which makes it way easier to configure, monitor, and troubleshoot the entire network.
It sounds like it would be incredibly powerful.
Yeah.
Especially for these really large, complex networks.
Oh, it is. And we can introduce new features and services a lot faster because we don't have to go and reconfigure every single router individually.
So it's like having a universal remote control for your whole network.
Yeah, exactly. And because the controller is software-based, we can use the power of software development to build these more dynamic and adaptable networks.
Oh, that opens up so many possibilities. You could program the network to respond to changing conditions, like automatically.
Exactly. Imagine networks that could automatically reroute traffic around any areas that are congested, or optimize themselves for different types of applications, or even defend themselves against security threats.
It really sounds like SDN is taking networking to a whole new level of intelligence and automation.
It really is. It's just one example of how the network layer is constantly evolving to keep up with the growing demands of our digital world.
Yeah, it's amazing to think about all the innovation that's happening behind the scenes to keep the internet running smoothly.
And to enable all those amazing applications and services that we all rely on every day.
Right, exactly. And before we wrap up part 2, I have one more question for our listeners out there.
All right, hit me with it.
So we've been talking about how important NAT is for extending the lifespan of IPv4. But what do you think about the transition to IPv6? Is it happening fast enough? Let us know in the comments. We're curious to hear your thoughts.
That's a great question. It's one that sparks a lot of debate in the networking community. The transition to IPv6 has been a long and complex process. There have been a lot of challenges and roadblocks along the way.
Yeah, for sure. And while IPv6 offers all these amazing advantages, like a practically unlimited address space and these enhanced security features, the reality is that IPv4 is still really deeply embedded in the internet's infrastructure.
Yeah, it's kind of like trying to replace the foundation of a house. While people are still living in it, you have to be super careful. And you have to coordinate everything really well, and it really needs to be a gradual, phased approach.
Yeah, I get it. But it sounds like we are making progress, though, right? More and more organizations are starting to deploy IPv6. And new devices are being manufactured with IPv6 support built in.
Yeah, it's a gradual shift, but it's definitely happening. And as the internet keeps growing and evolving, the need for IPv6 is only going to become more and more apparent.
Right. Makes sense. Well, we've covered a lot of ground in this part, looking at those complex routing protocols and that transformative potential of SDN.
It's been a fascinating journey through the very heart of the network layer.
But don't worry, there's still more to come.
In the final part of our deep dive, We're going to look at some of the more advanced features of routing protocols, and we're going to dive into the world of internet governance.
Welcome back to the final part of our deep dive into the network layer.
It's been quite a journey, hasn't it? We've gone from those bustling routers to the languages they use to communicate, and we even got a peek into the future of networking with SDN.
We did cover a lot, but there are still a few stops left on our itinerary. Let's start by looking at some of those advanced features of routing protocols, the ones we've been mentioning along the way.
Oh, you mean multipath routing and yeah, route aggregation. Exactly. Those are absolutely essential for managing the internet's massive scale and its complexity.
Multipath routing sounds pretty self-explanatory.
Yeah.
You just use multiple paths to get to the same destination.
Right. Yeah, that's the basic idea. Think of it like having different ways to get to work, in case one route is blocked by traffic or construction.
So it helps with network resilience and load balancing.
You got it. By spreading traffic across all those different paths, we can avoid creating bottlenecks, and we can make sure that the data keeps flowing smoothly.
Makes sense. So what about route aggregation? How does that help manage the complexity of the internet?
Okay, imagine for a second a map with every single house labeled individually. It would be so cluttered you wouldn't even be able to read it.
Yeah, that's true. Just trying to find anything on that map would be impossible.
Exactly. So route aggregation is kind of like grouping all those houses together into neighborhoods or city blocks.
Oh, I see. So instead of listing every single address, you just say, hey, this whole area.
Precisely. It makes those routing tables a lot smaller. It reduces the amount of information that those routers have to share with each other. And it makes those routing decisions much faster.
It's like decluttering the internet's giant address book.
Huh. I like that analogy. Those advanced features, they're absolutely crucial for keeping the internet running efficiently and reliably.
And we spent a lot of time talking about the technical stuff with the network layer, but there's also a whole human element to it.
Right.
That whole world of internet governance.
Oh, yes, absolutely. It's a really complex world. All those policies, regulations, all the different organizations that come together to decide how the internet actually operates.
Sounds kind of like the United Nations, but for the internet.
Haha. There are definitely some parallels there. Internet governance involves all these different stakeholders from all over the world. Governments, businesses, technical experts, civil society organizations.
And they all have to work together to address these huge issues like cybersecurity and net neutrality, and ensuring that everyone has access to the internet.
Exactly. And it's a constantly evolving landscape, too, because new challenges emerge all the time, and the technologies are always advancing.
Yeah, like how to deal with the implications of artificial intelligence.
Yeah.
Or the metaverse. I can only imagine how complicated that will be.
Yeah, it's going to be interesting to see how that all plays out. Internet governance, it plays such a crucial role in making sure that the internet remains free and open and accessible to everyone on the planet.
Right, it's a really good point. The internet isn't just all those wires and routers and data packets. It's a reflection of our values and our aspirations as a global society.
Well said. And speaking of challenges, managing and securing these networks is getting increasingly complex.
Yeah, especially with billions of devices connecting to the internet and all those new threats emerging all the time. I don't envy those network administrators. That's a big job.
It's a huge job, and it's only getting more difficult. It's a constant battle against those cyber attacks and the data breaches and the system failures.
It's like a never-ending game of whack-a-mole.
A really high-stakes game, too. Organizations are having to spend a ton of money investing in cybersecurity measures like firewalls, intrusion detection systems, and all that encryption stuff.
But it's not just about technology, though, is it? I've heard that a lot of those security breaches happen because of human error or social engineering, like those phishing scams.
Oh, absolutely. The human element is a huge factor, training employees on security best practices and just making everyone aware of things like those phishing scams. That's super important.
Right, so security is a shared responsibility. It takes both the technical safeguards and just having people who are aware of what's going on and being vigilant.
Okay. Before we wrap things up completely, let's take a super quick look at some of the emerging trends that are going to be shaping the future of the internet.
Ooh, this is always my favorite part. What's coming next? What's the next big thing?
Well, one trend that's really gaining some serious momentum is edge computing.
Edge computing. Is that kind of like cloud computing, but closer to the edge of the network?
You got it. Instead of relying on those big centralized data centers, edge computing brings the processing power closer to the devices that are actually generating the data.
So it's like having all these mini data centers.
Yeah.
Scattered all throughout the network.
Exactly. That reduces the latency, it improves the responsiveness, and it enables a whole bunch of new applications that need that real-time data processing.
Oh, right, like self-driving cars.
Yeah.
Or those augmented reality experiences.
Exactly. And another trend that goes hand in hand with edge computing is the Internet of Things, or IoT.
Oh, yeah, that's right, connecting all those everyday objects to the internet.
Yeah, everything from smart homes to those industrial sensors. The IoT is generating just massive amounts of data, and that data needs to be processed and analyzed.
And edge computing provides the infrastructure to handle all that data, much closer to where it's actually coming from.
Precisely. And those trends are driving a ton of innovation in the network layer. They're really pushing the boundaries of what's possible.
It's amazing when you think about it, how far we've come from those early days of the internet.
I know, right? It's mind-blowing. We've gone from those basic text-based websites to streaming high-definition video to controlling our homes from our smartphones. The internet has completely transformed our lives.
And it's all thanks to that invisible, but totally essential work of the network layer, making sure all those data packets find their way around the globe.
It has been quite a journey exploring this foundational layer of the internet.
Yeah, it really has. We've learned so much about the fundamentals of IP addressing and routing to that really complex world of internet governance, and then all those exciting things that are happening with the future of networking.
We hope you've enjoyed this deep dive and that you have a new appreciation for how the internet actually works. All those intricate details that make it all possible.
And hopefully we've sparked your curiosity to learn even more about this incredible, ever-evolving digital landscape.
If you like this episode, make sure to follow Explained. For more deep dives like this one, we'll be exploring all sorts of interesting topics from the world of technology and beyond.
And we're always looking for new topics to cover, so let us know down in the comments what you'd like to hear about next.
Until next time, keep exploring and stay curious.